which is here. All right, so here's the first chapter from this hands-on machine learning book. I highly recommend this stuff. I learned a lot from these books. I really want to go through the book and learn everything in here, and we'll talk later about the other things like Google Learning. So there's supervised learning and unsupervised learning to train a machine learning model. And then there's online learning versus batch learning, instance-based versus model-based, and we'll talk about this challenges and how to evaluate a machine learning system. So what is machine learning? It's actually a very good question to ask because it's not simple. This is the new way to program computers. Now, the idea here is getting a computer that learns to do something from the data by figuring it out without being told an algorithm. So instead of if you wanted to teach a computer to play tic-tac-toe, the old way was you would make some kind of algorithm where it like calculates some number from the board, which is the quality of your position, and it tries all the moves and picks the move that increases the maximum value of its position, that sort of thing. And then you have an algorithm that's written by a human, and the algorithm might not be right. And in machine learning, you don't do that at all. You just set up a series of neurons, simulated, that can store a relationship between the data coming from one and the data they send out, and you just let them practice playing until they try random moves until they win or lose, and every time they win, they try to remember to do things more that way, and every time they lose, they try to move in a direction to do less of whatever they just did, and they learn the way a human or an animal would learn, where they just try something over and over until they learn the system with nobody telling them what the rules are or what the strategies are. They develop their own strategies. That's what machine learning is. It's a very important new technique, and one of the best and worst things about it is you don't know how it works. So if machine learning model starts doing something you don't like, you do not know how to fix it. There's not an if statement you can add. There's not a bad line of code you can remove. You cannot say why it did that, and you cannot say what change would make it stop doing that. This is obviously a huge problem for security, and for that matter for functionality. You can train it, and then it has some degree of success at doing what you want, but some degree of error, and how to minimize the error and how to even measure and quantize the error is a topic of current research. So it's good for things like spam filters. You can just feed it a bunch of spam emails, get users to tell you when they're spam and regular emails, and then it will learn to tell the difference between spam and regular emails. It will make some decision about what's the best way to tell them apart. So that's called a model, the part that learns and makes predictions. And two ways to do it are neural networks and random forests. So why would you do this? In traditional programming, if you wanted to make a spam filter, you would make up a way to do it. Like you would go find words that appear often, and then you write an algorithm to check if those words are in there, and count how many times the bad words are in there, and then have a threshold value. If there's more than a certain number of those bad words, call it spam, otherwise it's not spam. This is the old-fashioned spam filter, Bayesian spam filtering. This is the way we used to do it. But in machine learning, and that's what it looks like here, you study the problem, you write rules, you evaluate it, analyze errors, continue doing this until it's good enough, and then you launch. The problem is, of course, when you have to add more rules, you just have to do this all over again. In machine learning, you study the problem, you train a machine learning model, you evaluate it, and figure out what's wrong with it. And once your machine learning model is working, then you launch. But you don't write the rules, and you don't maintain the rules. So the program can be more accurate, and it can be easier to maintain because you can continue to let it keep training on new stuff that comes in. All right, and you can make one that will automatically adapt. It can automatically be training, evaluating, and updating the data, so you can keep on adding more data all the time, so it will evolve with the changes of your spammers. All right, now some problems are too complex for traditional approaches or have no algorithm. We do not know any way to do them at all, so that would be a reason to try machine learning. For example, speech recognition. People have tried to isolate, particular pieces of a sound in speech, like edges in an image, and try to somehow figure out what the right way to recognize things are, but in fact just using machine learning seems to be the most effective way. Just give it a lot of recordings of speech and let the machine figure out how to tell one word from another. Another one, which is a bit more speculative to me, is that in principle, this is what science is, right? In science, you measure something like the pressure of a gas or the light coming out of a star, and then you end up with some kind of graph about how this varies with time or something, and then you try to fit some kind of equation through there, and you try to connect it to the known model, rules of physics and such, and make some kind of model. So you could think that maybe machine learning could help you do that. You could just train the machine learning model on something that you're interested in. It will figure out a solution, and then you could inspect the solution if you can deduce, what the mathematical equation is that does it. That part is not easy at all, but it is an interesting idea. This is what people like Ray Kurzweil talk about when they say we are going to move into an amazing new singularity age where the machines learn so fast that they outstrip the humans. And here would be the machine figuring out complicated things the human can't figure out, and then a human coming by later trying to understand how the machine did that. There's some of that going on. It's not a simple problem. All right. You can read our textbooks, ebooks. Yes, I think the O'Reilly, you might be able to get a free copy of the textbooks on O'Reilly. I don't know, that's possible. All right, so here's what machine learning is good for. Things where the existing solutions require a long list of rules or a lot of fine-tuning might be better off to just let the machine learning do that. A complex problem where we don't have a solution that works very well. A fluctuating environment where something keeps changing and therefore it would be easier. Good. Downloaded books and audio from the textbook is free, Tessa? That's interesting. If you put up a link where you got it for free, that'd be good to know. And then, anyway, getting insights about these complex problems, that's what that last thing was like. Perhaps you would like to actually understand your problem better after letting a machine learning model learn it. That's a little hard for me to follow, but I'm sure, I know people are working on it, but I'm skeptical about how well that works. Oh, okay, the O'Reilly site lets you download it. Good. All right. So, or libegen.rs. Okay, let me make a note of this. Free textbook. Libegen.rs. Okay, I don't know what that is. All right, I'll make a note of these things. If I can figure out what they are, I'll try and add them someplace so other people can figure out how to get a free copy of the book. Some students have done it. All right. So here's some examples. If you want to look at products on a production line to pick out the defective ones, that's image classification, and that typically uses something called convolutional neural networks or transformers, which we'll talk about these in later chapters in more detail. Detecting tumors and other things in brain scans, x-rays, classifying news articles. You might want to sort them by topic. Now that requires understanding language, and that's natural language processing, which we're going to talk a lot about in the large language models. The main product thing that makes those work is transformers. Good. All right. And then you can make a chatbot, we talked about, or personal assistant. Opera supposedly, I think it's Opera, now has an assistant. Some computer company, I can't remember which one, now has a large language model assistant that can see every window on your desktop and sends it off to some model. And people say that might be a privacy risk, but it'll offer to help you with everything. Anyway, forecasting financial revenue based on performance metrics, reacting to voice commands, detecting credit card fraud. It's a matter of detecting unusual transactions among all the others. Taking clients that come to your company or visitors to your webpage and just sorting them into groups so you can then try to give them marketing strategies. Representing a complex data set and making a clear diagram of it, another machine learning task you could use. Figuring out what product to recommend at Amazon or Netflix, these other places, based on past purchases. That's another thing that would be machine learning would help with. Building bots to play games or to play a role in a game. These are all common applications for machine learning. So here's some types of systems. There are various ways to do it. One way to categorize a machine learning system is how it is supervised during training, and there's various versions of that. Supervision means that you tell it what the right answer is for the training data, so it learns to detect that. Unsupervised, you use data that is not labeled, so you don't know, and there's other versions. Then whether they learn incrementally or on the fly, batch learning is what's happening with ChatGPT. It was all trained on the internet up to a certain time, like 2021, and it doesn't have any data after that. That's one way that's a batch learning. You have one batch of training and that's it. Online learning lets it keep learning more and more and more as time goes on. And then you can work by comparing new data points to known data points, or by detecting patterns and building a predictive model. Those are called instance-based versus model-based learning. Those are two different ways to learn from your test data, from your training data, that you can apply later to test data. So here's the types of training supervision. And we'll go through them one by one. The simplest and most obvious is supervised learning. You have data that comes in with labels, like pictures. Some of them are pictures of a cat and some are pictures of a dog, and they're all labeled. This is a cat, this is a dog. Then you train your model on that, and it can practice until it gets good at telling what is it in common among those cat pictures, so I can label the cats that makes them different than the dog pictures. And now when you show it a new picture, it will have some ability to tell whether it's a cat or a dog. So you sort inputs into categories, and then you do some kind of fitting. Now, that's one task, classification. Another one is regression, where you have some kind of graph of data, one feature related to another, and you're going to fit some kind of curve through this to find the pattern, so you can then predict values. So this is that's called regression. All right, so unsupervised learning, the training data just comes in and it is unlabeled. You do not have it pre-sorted into any meaningful categories, and yet it might cluster in some ways. There's a cluster of people down here and people up here, not very many people here, people there. So there are some groups here. It's not just random, but you don't have a label attached to them. So one thing you can do is just break them into groups, clustering them. This is the step one of science. Every science starts by observing something like animals or weather, and then you do taxonomy, where you just sort them. Well, these animals are the same, those animals are different, that sort of thing. All right. You can then visualize it perhaps, sort them into categories and give them different colors and show how they overlap in some way. That's one way to understand. Yes, this is all being recorded. All right, then another issue you might have to do is dimensionality reduction. If you have too many different properties for each sample data to where it seems unnecessary, then you might merge correlated features into one, just to make a lower amount of complexity in the data, something you often do before training it, if your training is getting confused. So for example, if you have cars, you might have mileage and age, which is how many years old the car is and how many miles it is. Well, those are probably very strongly correlated, so you could just combine them into something called wear and tear. And that's called feature extraction, where you take the input data and you decide to extract more meaningful, simpler features, so you can have a smaller number of parameters that you measure from each input point, to make it easier for the model to find patterns. And we'll do quite a bit of that as we go ahead. So unsupervised learning, one obvious case is anomaly detection. You have data here, and most of the data is here. This is normal data, and you have, when you get a new one, you can see, well, it's pretty far from the average. And we're going to use this as a defense mechanism to protect neural net models later. This anomaly detection is useful. Is it like factor analysis? Well, I don't really know what factor analysis is. I know what we're going to do later with some housing data is we're going to show that if you calculate how much the thing you want to predict is correlated with various input parameters, it turns out that by combining them you can make something that's even more correlated than any of them alone. So I'm not sure if you call that factor analysis. Yeah, I think it is all related to that. I just don't know. I don't know all the terms. But combining the input parameters to make new synthetic parameters that are more correlated with what you want is an important process with several names, and I don't know the subtleties of the different versions. All right, another thing you can do is try to find interesting relations between attributes. So if you have I remember when I first saw the Safeway loyalty card, must be 15, 20 years ago, I was a database analyst. And I looked at that and I said, wow, if you had that data, you would know what everybody bought, when they bought it, how often they bought the same thing, what time of day they bought it, what physical location. You could do all kinds of interesting things with that data, and they're doing it. And so you can ask yourself, if you have a database, like from loyalty cards, what people have bought, do people buy certain things together? Should you make like a special where you sell the hamburgers and the beer as a combined special because many people buy these things together, something like that. So you can do that with unlabeled data. You can notice patterns in the data that might be useful to you. And then there's semi-supervised learning. So first you have unsupervised data without any labels. Then you sort it into classes. Then you can ask the user to tell you this whole class should have a name and this whole class should have a name. So they did this with images on image websites. You'd have many images of the same person. You'd use unsupervised learning to group them together and then say, okay, here's 10 pictures of this guy. What's this guy's name? And then just one fact, you can then add a label to it, and now you have labeled data. So that's one way to do it. And then there's self-supervised learning, which sounds nuts, but this is how the image generating websites work, like Stable Diffusion. So you have images that are not labeled, then you just cover up part of the image, and now you've labeled it in the sense that you know this is the partially redacted image, and this is the unredacted image, and you train your model to unredact an image now, so it can fill in a gap. And Stable Diffusion works by adding noise to an image and training your model to remove that noise. So you synthetically create labeled data from unlabeled data by modifying it. And then there's reinforcement learning, probably the first case I ever thought of for machine learning, learning how to play games. Or, for example, drive a car, have a robot walk. You do something, and then at the end you get a reward or a penalty telling you whether you did it right. And then you try it again and try it again. And the rewards or penalties are what acts as the label to reinforce it and teach it to do it right. So that's another way to do it. And so here the robot observes something, selects an action, does something, then it gets a penalty. Nope, you shouldn't have gone for the fire, so it is bad, next time avoid it. So that's the point. You learn with many patterns, just like an animal would learn, like traversing a maze trying to get a reward. All right, let's take a look at the Kahoot for this stuff. These Kahoots are in-class quizzes that are worth extra credit. If you get in the top 3, you get 3 points. So let's try this. The main point of them is to stop people from falling asleep during the lecture, however. And someone says they made an AI that can play Valorant, whatever that is. I know they can play chess. And many other games, Go and so on. So I know machine learning has gotten to the point where it's beating humans at many of the traditional human games. To do the Kahoot, you go to kahoot.it, and you type in this game number. Good, good. I see someone putting the instructions in the chat. Good. All right. Yep. I'll give it a few more seconds. People may still be coming. All right, let's give it a shot. Oh, all right. All right, so what part of the system learns and makes predictions? That's what's called the model. All right. All right. So what system might mask part of an image to generate a labeled data set? All right, that's called self-supervised. You take unlabeled data and you modify it to create labeled data. It's one of the strange situations where you actually feed data into machine learning that was created by machines. All right. All right, what system needs labeled data for training? Those are the supervised models. The simplest ones, you give them examples of what you're trying to achieve that are properly labeled so it can learn to apply those labels to new images. All right, what system learns to play a game based on rewards and penalties? That's reinforcement learning. All right. So, Greg, all right. And Woot. Oh, who that is from BibFast, I think. And Kate, all right. And if those names match names you put it in the canvas, we'll be able to award you your points. All right. I'm going to stop this recording.